We are the non-rigid rifle recoil rig, and this is our final design review. My name is Trevor Johnson. I am joined by Sam Danka, Alex Agers, and Bradley Vandervoort. We would like to thank Dr. Carl Frick and Dr. Ray Fertig for sponsoring this project. Here's a quick agenda of what we'll be covering today. We'll start with our project summary, then our engineering analysis, our fabrication, our testing, our results, and finally our conclusions. So the main problem is that the connection between perceived felt recoil and the actual force exerted on a person is not well understood. This problem extends beyond our client's needs and encompasses further social and political issues such as inclusivity and ethical hunting. Many smaller individuals shy away from gun sports because they profoundly feel the effects of recoil. Additionally, working to reduce recoil will allow many hunters more comfortably shoot large caliber firearms, which are more appropriate for the ethical hunting of big game. Next, looking towards our clients' needs, they wanted us to create a device that's designed to collect data and better understand rifle recoil. This device needed to be able to approximate a human shoulder experiencing rifle recoil, needed to provide a repeatable way to gather force and displacement data, and there needed to be an ability to test for different size shooters. To get started, we looked at a few different past solutions at looking at rifle recoil. Down at the left, we have a rig created at Cal Poly, and at the right, we have a rig created by gun enthusiast Cal Zant. The key feature on both of these rigs is that the recoil is measured against a fixed support. Uniquely, our design will be mounted on linear rails, allowing for there to be a displacement when the gun is fired, which more accurately mimics the action of a human shoulder. So there are a number of project requirements that we had to hit, starting with our high priority requirements. We wanted to keep the sliding portion of the rig below 8 pounds to keep it in line with the weight of the gun. It needed to be able to hold up to 200 pounds. We wanted it to be adjustable to fit a wide variety of firearms. It needed to be stable, and we wanted to approximate displacement data from previous human trials. For our medium priority requirements, we needed to include a damping mechanism, and we wanted to make it easy to transport. And finally, for our low priority requirements, we wanted to make it simple to maintain. Now we would like to show a short video demonstrating the key features of the non-rigid recoil rig.
The non-rigid recoil test rig prototype is a 5-foot-long, 2-foot-wide device designed to simulate a human shoulder for the purpose of measuring perceived recoil. The overall construction consists of a sled mounted on 2 parallel linear rails, which are in turn attached to a 2-inch aluminum T-slot base. The protruding arms of the base have a plastic covering to help increase the friction between the rig and the surface it is being tested on. These arms can also serve as a surface to lay sandbags down onto to weigh down the rig while in use. One of the benefits of using aluminum T-slot is its ease of assembly. A single set of Allen keys is all that is needed to fully assemble and disassemble the entire test rig. To simulate the mechanical behavior of a human shoulder, a spring system was implemented. The spring is attached to an eye bolt on the sled via a carabiner. The other end is then attached to an eye bolt fixed to an aluminum T-slot base. This system allows for a high level of customization, as different springs can be easily interchanged in a quick amount of time. The next components are rail bumpers. Featured at both the front and the rear of the rails, these assemblies consist of an aluminum stopper and foam cushion. The aluminum stoppers can be easily adjusted with an Allen key, and the foam cushions are cut to fit over the rail. The sliding portion of the test rig is a crucial assembly. Weighing in at just under 8 pounds, it consists of the gun mounts and a butt plate attached to an aluminum frame. The sled butt plate consists of a reinforced aluminum T-slot member, piezoelectric load cells, and aluminum backplate. To adjust for different shaped rifles, the load cell mounts can be vertically adjusted. The sled also contains 2 vertical gun supports. These are fabricated out of aluminum plating and low-profile aluminum T-slot. To account for various gun geometries, these supports can be adjusted both horizontally and vertically with the help of an Allen key. To mount a gun into the test rig, it is first placed onto vertical supports. These are then adjusted to fit the rifle. For display purposes, we are only using the rifle gun stock. The rifle is then strapped to the butt plate using a harness, and the gun is then strapped at the gun supports. To simulate different size shooters, 10-pound steel plates were fabricated. To add to the test rig, they are slipped over the vertical aluminum posts and then clamped down using quick-release weight collars. To remove the weights, the process is merely reversed. 20 plates were fabricated in total, allowing for up to 200 pounds of added weight to be tested. At the other end of the spectrum, the vertical aluminum weight posts can be removed from the sled to test a weight under 8 pounds.
Now that we better understand the key features of the non-rigid recoil rig, we can move on to our project timeline to see how we got to this point. So here in this diagram, the colors represent the individuals who are working on each component of the design. Initially, we focused the majority of our efforts on working on our shoulder model. Then as we began to progress through this, we were able to begin our engineering analysis. As we began to flesh out our design, we were able to create a SolidWorks model. From there, we were able to begin our fabrication, our assembly, and eventually our final testing. We estimate the total manpower hour on this project was approximately 250 hours. Now I'll pass it over to Alex to talk about our engineering challenges.
Yes, so yeah, now that we had our product requirements set up, we were able to begin our design process. And during this design process, we faced three big challenges. The first, how to mechanically model a human shoulder following our given displacement curves, how to actually build a weight sled that weighs 8 pounds, but can hold up to 200 pounds of added weight, and can we design a test rig that can handle the extreme forces of the rifle? Beginning with the shoulder model, we started with this displacement curve over the summer, and our goal was to create a simulated shoulder mass to follow this displacement curve. As you can see in this displacement curve, there is a steep initial slope that goes and tapers off to a flatter, shallower slope. At the beginning of our design process, we reached out to Dr. Boyd Dye from the UW biomechanical department to kind of interpret this graph for us. And so what he told us was that that initial slope was from what are known as more the passive elements of the shoulder. And those include like your ligaments and your skeletal structure. And that's what we can mechanically model. So after a few different design iterations, we settled on this second photo here, and that is our system. It begins with the mass of the gun, a spring that represents the recoil pad at the end of a rifle, the mass of the sled, which is going to be our simulated shoulder mass, and then another spring that is used to model those passive elements. Solving for that system resulted in this equation here. The N, H, F, and G values are all constants, and additionally we included the initial velocity of the rifle. When we went to go plot this equation, we knew that the initial velocity of the rifle was 3.2 meters per second. In addition, we knew what the mass of the rifle was and our range of masses for the mass of the shoulder. We approximated the recoil pad as a linear spring based off some given data we had on those. And then really what we had to do was just tinker with our second mass and our spring value to see what type of behavior we saw. We were able to find that actually there are some combinations that give us that initial slope we want to see. So with that, I'm going to hand things back over to Trevor.
Sorry about that. Thank you, Alex. Here we have an image of our SolidWorks model to highlight the key areas where we had to perform our engineering analysis. The first key areas are aluminum crosslinks that provide the support for our gun mount assembly. Then we wanted to look at our 2x2 T-slot framing, which forms our base. And finally, we wanted to look at our butt plate assembly. In order to analyze aluminum crosslink connectors, we looked at the force inputs to the gun mount assembly. Here our input force is 1,600 pounds, which is the maximum recoil force we expected to see from the firearms. From this, we were able to determine the bending stresses and additional shear stresses due to torsion and the aluminum crosslink members. we could combine these stress states and determine the principal stresses from Moore's circle. Then using our principal stresses, we could compare these to the Tresca failure criterion, and we found that we had a factor of safety of 2.15. Next, we performed a binning analysis on the 2x2 T-slot framing that forms our base. Here our applied load is 100 pounds. That's because when our rig is fully loaded with 200 pounds, there's 100 pounds on each side. From this, we're able to determine our maximum bending stress, our maximum shear stress, and our maximum deflection, and compare these to our maximum allowable values. As you can see, all of our actual values were much lower than the allowable, resulting in a factor of safety of 8.5. With that, I'll pass it over to Bradley to talk about the analysis of the butt plate assembly.
Thank you, Trevor. In order to analyze the butt plate assembly, we had to do a bending analysis on this vertical member. We first did this analysis with that force equal to 1,600 pounds, which is P right here, at a height of 4.5 inches. We're using max allowable deflection, max deflection. We got a factor of safety of 1.27. But we also ran that analysis at our worst case scenario, which is the force being applied at H equal to 6.5 inches. With that, we actually failed. We had a factor of safety of 0.6. Therefore, we concluded we had to add something to make it more stable. We added this angle member right here. We ran 2 additional analyses on that. One was a bending analysis, which resulted in a max stress of negative 12.47 KSI. Using max yield stress, we got a factor of safety of 2.8 on that one. And then we also did a buckling analysis on that, using Euler's critical load equation for buckling. With that analysis, we got a critical force of 835,000 pounds, giving us a factor of safety of 369. Moving from the engineering analysis, we'll talk about fabrication. With fabrication, we had 3 main materials, the first one being aluminum. In order to fabricate the aluminum, we used the machine shop saw, milling machine, drill press, and lathe. And then we also had steel for the steel weights. We water jetted those to save time. And then we also had those TPU plastic end sleeves that we talked about, and we 3D printed those. With that, I'll hand it over to Alex to talk about testing.
Yeah, so now that we had finished our fabrication, we were ready to begin testing. But before we could start that testing, we had to consider safety. So the use of a firearm in our test rig means that strict gun safety had to be adhered to. This meant establishing a firing line, treating the weapon as if it's loaded at all times, and practicing proper trigger discipline. In addition, we would wear personal protective equipment. This included hearing protection, eye protection, and masks, of course. In addition, we established a safety officer, that being Dr. Fertig. And we also wanted to follow codes 13.1.1 and 13.5 of the general range standards. And these require us to inspect our danger zone, and in addition, not to tamper with the rifle if it is loaded in the test rig. So this is just a photo of us setting up for a test. Our testing included us doing a variety of weights and springs in our test rig. If we look here, we can see Trevor standing by the back of the pickup truck with a laptop. He's recording our force versus time displacement from our load cells, and Bradley's looking down through a high-speed camera, which we use to measure our displacement versus time data. So here we wanted to show you a quick video of one of our tests. This is with our lightest weight and highest or lowest spring.
Trevor. Good? Yeah. All right, fire.
With that, I'm going to hand things over to Sam to discuss our results.
All right, thank you, Alex. So yeah, on the right here, we're going to just start with force versus time. This is a sample plot for one of our tests. Basically, it's just a summation of the 2 load cells that we used. And at that dot at the very top, that is our peak force, and that's right around 6,000 newtons across most of the tests, and that's what we expected given our provided data. So when we go on to the next slide, what we do is we plot each peak force value from each test on the same slide, and really the point is just to observe that there are some trends. One of these trends is that within the same spring, as you increase the mass, we experience a greater peak force. And then as you look across from left to right, we're actually increasing the spring stiffness. And we noticed from our data that altering the spring stiffness had no effect on the peak force. So it'll be interesting with further testing to see if there's some sort of trend that we can discover there, but for now there was not. Moving on to the next slide, we're going to look at our displacement versus time data. To collect this, we use a high-speed camera at 1800 frames per second. This gave us plenty of data points so that we could get a smooth displacement curve. So basically when we watched this video, this was actually a software developed by a graduate student here, Mitchell Anderson. And basically that white line holds onto an edge and tracks it across the screen, and it's able to count how many pixels it displaced. And then based off of us providing the software with a scale, it can convert those pixels to millimeters. So if it displaces 20 pixels, then it's approximately 20 millimeters. And that's dependent on the field of view. So if you want to improve that resolution, you just have to make the field of view smaller. Moving on to the next slide, we have a similar graph to that of the force, but now we're looking at max displacement. Here you can see that the springs do play a major role as expected, and that as you increase spring stiffness, you reduce the max displacement. And similarly, as you increase the mass, you also reduce the max displacement. So on to the next slide, we're looking at displacement curve. This is the same spring, it's a medium stiff spring, and all we're doing here is increasing the mass and observing that the displacement decreases. But more importantly on this slide is to notice the way that the curve behaves, similar to how Alex talked about when we were given that provided data. We wanted this bilinear curve with the steeper slope that transitioned into a much shallower slope. And we can actually see that on the next slide where we have a video. This video is a high-speed footage for test 200 pounds with a medium spring stiffness. And what's critical to observe here is the initial impulse where there is minimal displacement but occurring at a very high speed, and then it transitions to a steady displacement where we have much more displacement but at a much slower rate. So as we push play, as the rifle's fired, big initial impulse right there. Do you want to try it again, Bradley? So yeah, as we push play, big initial impulse as the rifle's fired, and then over the next 50 or so seconds, we just get quite a bit of displacement, but occurring at a slow and steady rate. So this is very cool because we want to compare this to our human trials from last summer. This is actually a team member of ours, Bradley, and this is him shooting a rifle, and you'll see the same thing. As the gun is fired, there's this huge fast impulse as there's minimal displacement. And then over time, as Bradley's head and chest begin to catch up to the load, it begins to displace much more, but over a more steady period of time. So as we let the video run out, you see all that extra displacement at the end. So to put all this together, we went ahead and plotted our model of the spring mass combinations, and those are in blue, and we overlaid that over our human trials from last summer in red. And we can see that our system, with our modular system, we are able to identify various spring mass combinations that can mimic human displacement. So with that being said, we'll pass it on to Bradley to talk about some more of the successes of the project.
Yeah, thank you, Sam. We accomplished a great many things with this project. One of those things is that we made a product capable of collecting that repeatable force versus time and displacement versus time data that our clients were looking for. We also created a sliding portion of our test rig that was less than 8 pounds. That was really important. We made a design that was able to support the added 200 pounds of weight to simulate different shooters. And we also were able to make a non-rigid test rig that was convenient to transport, simple to adjust, and easy to maintain. Lastly, we built a highly customizable product that can easily be adjusted for any future needs. We also were very successful in our budget. We were given an estimate about $2,000 from our sponsors at the beginning of the project, and we actually only spent about $1,060. So we're very happy about that too. Although we did a great job with our project, we do have some recommendations going forward. First off is that we would increase the distance between these aluminum crosslinks. That would be mostly for moment interactions, but also for this barrel overhang that just isn't really necessary. Second, we'd attach a wire clip back here. When we were testing, we saw that the load cell wires tended to get in the way, and we wanted to make sure that those don't get damaged. So putting a wire clip there is the best solution that we have. 3 would be further increase the overall adjustability. We see these gun mounts right here. We think that we could maybe do some sort of crescent wrench style or vice grip style grips to further accommodate different wider stocks that we need to. 4th would be to improve the remote trigger system, and 5th would be to continue to research the shoulder model. With that said, I'd like to thank everyone here. First, we'd like to thank our sponsors, Dr. Frick and Dr. Fertig. Then we'd like to thank our instructors, Dr. Kuhn and Dr. Nahn. We'd like to give a special thanks to grad student Mitchell Anderson for all the work and effort he's put into this project to help us out. I'd like to thank Ike Roos for his design input and help on engineering calculations. I'd like to thank Spencer Miller and Gary Pulse for their help in the machine shop. And then Dr. Boyd Dye and Dr. Nico Ian for their input on the mechanical shoulder model. Lastly, we'd like to thank you all judges for spending the time to be here. We'd like to open up to any questions at this time if you have any.
Questions from the judges?
Yeah, I have one. So did you consider design alternatives or like how, I mean, it seems like a fairly nice design, but what, can you talk a little bit about the iterations that were required to end up at this design?
Yeah, we'll go back
Or
to
it's
the
just
solid.
one, you know, you don't, I mean, probably there were more.
I was trying to go back to this model. Yeah, Ike Roos was on this project in the summer of 2020, and he came up with a design where it was just one support frame, and then the rails were on the side. And so we looked at that model, and we came up with a different model because we wanted it to be more robust in the end, and also just to have a different loading on these rails. Instead of having like a more shear, we'd have more of a compressive load. So that was one thing we did here with the SolidWorks, the actual model itself. But we also ran through several iterations with this model itself, and I'll actually give it to Alex to talk about that.
Yeah, so we actually spent if we looked at our timeline, we spent a large majority of our first semester going over this model here. And originally, we didn't really know where to start just from this curve. We were a little stumped, but we tried a lot of different things. Originally, we had some pretty complex systems that included like multiple, like 3 masses, a lot of like spring damper systems. And then after that, we were considering, instead of using like a spring to model those passive components at the end, we were going to use a damper system or a delayed damper system of some kind. But, you know, we then talked to our sponsors a bit more, and the whole spring at the end here was mostly from their advice as far as what we did. The behavior we see is that curve is from having that secondary spring being much lighter than that first spring, and that still gives us that somewhat of like what looks sort of like a dampened curve shape. So that's how we ended up at our final iteration there.
I'll just add one final note, and that's simply that one thing that we liked about this design was that it allowed us that in the future, if we did want to add further complexity and say add another spring or something like that, it would be very easy for us to incorporate additional springs into the design.
All right, thanks.
We have time for maybe one more quick question.
Yeah, I've got a question for you guys. Did you run multiple tests at, say, a single condition, single set of mass and springs to understand your uncertainty or variability at a single set point?
Yeah, if you go down to the, Bradley, you know the graph. Actually here we're showing both test 1 and, here I'll let them get there first. Actually here we are showing test 1 and test 2 back to back for most of these. So some of the variability you see, like for example, spring E actually is just the same weight and the same spring. And so you can kind of see the variability there. We weren't able to just run like as many tests as we wanted to due to like ammo concerns and stuff like that. But if you look at this graph for a little bit, you can kind of see some of the variability. And, you know, some of that has to do with just the different amount of ammo and things of that nature. But, and, you know, sorry, I'm trying to think of the word, but just basically the load cell being able to have the same repeatability.
Any final questions?
So a quick question from Xiang here. So when you're doing that analysis, right, you decided your analysis lead to the conclusion to add that support on the back, that 45 degree, right? In those analyses, I'm just curious, have you, because I see a lot of bolts and also possibly, I guess somewhere there may be like welding as well. When doing that analysis, do you take any consideration of those things, which make your analysis like either more complicated or you make it like higher stress, for example?
I think that what you're saying is, sorry, for some reason I can't click, saying like maybe any welding interactions here that would probably contribute to sort of like a moment added.
Yeah,
we didn't really, sorry, go ahead.
Yeah, please, yeah. So basically, I'm asking, have you just considered any of those impacts?
No, we just went straight for the simple I guess we just simplified it down to this like fixed beam on this analysis, and same thing with this one was just a fixed beam cantilevered.
I see. Yeah, thank you.